Okay, well, welcome. This is the tutorial on log linear models and conditional random fields. And before I get started, there's a low number of you here in the audience. So I think I'd like to sort of maximize the benefit for everyone. So first thing I'd like to do is ask you to come and sit closer because I'm going to be using the whiteboard. And the second thing that I'd like you to do is introduce yourselves. I'm going to be doing this like the graduate classes that I teach rather than like what might be a conventional conference tutorial. So I don't have any PowerPoints. These are the lecture notes that I use for my graduate class or part of my graduate class. And I'm going to be going over them pretty slowly. Would you mind coming and sitting here maybe so that then I have a smaller field of view? I'm really wondering if anybody else is going to come. The organizers, I'm sure they were very busy. They didn't tell me how many people there were going to be beyond the fact that not many people were pre-registering for tutorials. And then a few minutes ago, I thought somebody told me that there were going to be 10 of you. That I'm just wondering. And I hope that that the level that I have planned for this, which is the level of my first year graduate class, is going to be a reasonable level for those of you who are here. But so let me. I want this to be interactive. I want you to ask questions. And so let's start by just finding out who we are, since there are only 4 of you. So why don't we start with you?
Hello everyone. My name is Eric Liu. I'm from the University of Cambridge, the one in the UK.
Oh, and what do you do at Cambridge University?
I do wireless network modeling, stochastic.
Wireless network modeling. And are you a faculty member?
Oh, not yet.
Not yet? So, postdoc. Okay, where's your PhD from?
In the same place too.
Cambridge, okay.
I got lazy afterwards. So.
Yeah, I was an undergraduate at Cambridge. Were you? So, were you an undergraduate at Cambridge?
No.
No, okay.
I did my PhD there.
Yeah, because I was an undergraduate there, and then I could have been lazy and I could have stayed there for my PhD, but actually I decided not to. But it's a great place. Welcome. You said it was Eric?
Yeah.
Eric, great. Hi.
I'm David Butler.
Yes.
I'm from Lawrence Livermore National Lab.
Okay.
I'm working there on doing things like text mining,
Yes.
reference resolution.
Right. And do you have any previous experience with conditional random fields?
I've used them a lot.
Okay. And in what form have you used them? As a software package?
Yeah,
or?
mostly just as a software package.
Uh-huh. Which software package?
Been using the Stanford Named Entity Recognizer.
Okay. That's from Chris Manning and his group, yeah. How's that worked out for you?
It's been better than any other model that we've tried. So better than like the lane pipe models or some of the commercial tools that we've tried.
Yes. So being better in accuracy?
Yeah, right.
Yeah,
Definitely.
okay.
It's been a little bit painful to train it in different, for different entity types, but other than that, it's been pretty good.
Uh-huh. And have you tried any alternatives, like Mallet from Andrew McCallum's group at University of Massachusetts, for example?
No, I haven't tried that one.
Okay.
But we had tried several other ones, like OpenNLP and LinkPipe.
Okay.
Those aren't CRS. So.
Okay. So I would, I've had students who have occasionally tried to compare different packages, and they've had, I'd say the conclusions have been mixed, and the conclusions may have been mostly due to their familiarity with the packages. But there's 2 that I would recommend, and this could be interesting. There's a package called CRF++, which, as the name suggests, is written in C++. And I don't quite remember the name of the author, but he's a researcher in Japan. And this is essentially a standalone implementation of conditional random fields. Okay. And it's fast and easy to use. Now, what it doesn't have it doesn't implement any other tools that you might want to use for linguistic analysis. But if you just want to do linear chain conditional random fields, then CRF++ is easy to use, reliable, fast. And then there's a newer package called CRF SGD, where SGD stands for stochastic gradient descent. And the main author of this is a researcher called Léon Botou, who's at NEC Labs in New Jersey. But this is, you can just Google for CRF SGD, and it's, I think it's also written in C++, but the nice thing about it is that the input-output format for the data is exactly the same as for CRF++. They are plug compatible. But it uses stochastic gradient descent, which is pretty much the latest and greatest training method for conditional random fields. And in the experience of my students, this package is several times faster than this one. And this one is already very fast and usable. So this would be the package that I would recommend as an implementation of the ideas that I'm going to be talking about in this tutorial. And there are other software packages, notably Mallet is the one that I have the most familiarity with, although not a lot of familiarity, which is from Andrew McCallum. Andrew is a professor at the University of Massachusetts in Amherst. He's one of the 3 co-inventors of conditional random fields. And Mallet is a pretty comprehensive package for doing a lot of text analysis tasks. I have a bias. Mallet is written in Java, and somehow I've never had very good experiences with software written in Java. It's always seemed to be slow and clunky, and not nearly as platform independent as it should be. But maybe other people have better experiences with Java than I do. And certainly Mallet is a pretty widely used package. So, sorry, what was your first name? David, and you're from Livermore?
Yes.
Yeah, great. Hi.
Hi, I'm Lisa Friedland, and I'm actually at UMass Amherst.
Oh, okay.
Andrew McCallum, but David Johnson. In a data mining group. I'm a graduate student.
Okay.
In a data mining group, we do relational data.
Yes,
data.
yes. Okay, so I know David pretty well, and I think that if you've taken Andrew's class from Andrew, then probably nothing that I'm going to say is going to be very interesting or novel. But if you haven't, then I think I'm going to be presenting log linear models and conditional random fields in as concrete a way as possible. I want to make them elegant because I think they are elegant, but I want to leave off everything that makes them seem more complicated than they need to be. And to explain the sort of what I'm trying to get at. So these are lectures that I give in my pretty much lectures that I give in my graduate class for first-year graduate students, and then the assignment that they have to do is a mini project where they have to implement conditional random fields. And they're not supposed to be using any package, because what I don't want is for them to be consumers of conditional random fields. I want them to understand how they work concretely enough that they can implement the algorithms. So I want to teach the simplest possible version of the algorithms. And then if they want to, they can then go on and be users of conditional random fields, and they might use an existing package because it has good software engineering and so on, but they're going to be very well-informed users. And then they might also, or they might choose to go in the direction of designing, implementing some variation on conditional random fields that would be novel research. But I really want them to get a hands-on understanding. Okay, and it was Lisa. Hi. Hi.
I'm Rakesh Agrawal.
Hi,
I work
Rakesh.
for Microsoft Research.
Yes. Yeah.
In Mountain View.
Uh-huh.
I just thought I'd come and learn
Yeah.
about conditional random.
Yeah, great. Have you ever used conditional random fields before? Or?
Not me personally, but some of my colleagues use
Yes.
it.
Yeah.
And we had trouble scaling it,
Uh-huh.
making it use it on the web scale. scale?
Oh, okay. So as far as I know, conditional random fields are potentially scalable because they're really an extension and generalization of logistic regression. And logistic regression certainly can be scaled. And actually, I'm going to be talking quite a bit about stochastic gradient as a training method, and that has some really major scalability advantages. And well, I haven't done scalability experiments with this package, and Leon Botu is certainly an expert on scalability, so it might be a research question to make conditional random fields even more scalable than this implementation, but there is the potential, and I think it's certainly an important research topic. And conditional random fields are a supervised learning method, and so you have input examples, and the input examples are represented in terms of features. And it's routine to have hundreds of thousands of features for each input example. And it's certainly routine to have tens of thousands of training examples. I have a student who's done a project where using tens of thousands of training examples and hundreds of thousands of features for each training example. Of course, when you have hundreds of thousands of features, so speaking intuitively, the great majority of those features are switched off for every example. So if you have 100,000 sort of non-trivial features for every 100,000 non-trivial features for every training example, that's probably going to not scale. But if you think of the analogy would be each training example is a document, and then each feature is a word in your dictionary. So you might have 60,000 words in your dictionary, and then for any particular document, only a few of those words are present, so only a few of those features are switched on. And if most features are switched off for most examples, then tens of thousands of training examples, hundreds of thousands of features is certainly computationally feasible. And there's a lot of opportunity, I think, to scale up the feasibility by further orders of magnitude. And I think what I'm going to be talking about today is a good basis for how to think about conditional random fields so that you can start thinking about scaling them up. So that's an example of what I mean by wanting to give students in my graduate class the foundation where they can then think about research questions that would push conditional random fields forward. Okay, I think we got one more person who came in. Hi.
Thompson Mr. Sagos, I work for Yahoo Research.
Okay.
Advertising science.
Yeah, in Mountain View? Yeah. Yeah. And have you used conditional random fields or any way you've come across them? Or?
Yeah, a little bit, but more in the logistic regression and
Okay.
linear models.
Okay. Did you use well, so did you use a software package or did you write your own software? Or?
Wrote around.
Okay.
One of the main concerns is scalability.
Okay. Did you use stochastic gradient training or what did you use for training?
No, we used standard methods for, we just used gradient descent or improved iterative scaling.
Okay. As far as I know, improved iterative scaling is definitely not the state-of-the-art method for training anymore. And the conventional opinion for what the state-of-the-art now is something called LBFGS. So L stands for limited memory. BFGS, I think all four initials stand for the names of the authors who are researchers in mathematical optimization. And this is a gradient descent training method, but it operates on it's a conventional optimization method in the sense that it operates on the gradient of the entire objective function. And the entire objective function depends on all the training data. So this method, essentially, you need to have all the training data in memory, and then you need to compute the gradient over all the training data before you can take even one step towards optimizing your objective function. So it's not useful if your training data are streaming in and don't fit in memory. And if you have, if you, intuitively, the more training examples you have, the more information you have. And you only need a certain amount of information to train your model. So if you have a model that only has a few parameters and you have millions of training examples, and the training examples come in a random order, then intuitively you should be able to train your model without even using all the training examples. And stochastic gradient descent has this property, it has this advantage, that you can begin training your model after the first training example, and you may get a well-trained model before you've even seen all your training examples. And stochastic gradient descent is, it's easy to implement, and it's easy to adapt to slightly different training objectives or whatever, whereas BFGS is a real tour de force of numerical mathematics, and there are some excellent package implementations of it, but I don't think many people interested in data mining or machine learning would want to try to do their own implementation of it. You said your first name was Tassus?
Yeah.
Hi. Okay, so I think I can get started. Actually, another prop that I'm used to that I don't have in here is a clock. So the way we're organized, I think we have 4 sessions from 11 to 12:30, and then lunch break, and then 1:30 to 3, 3:30 to 5, 5:30 to 7. And I do tend to go rather slowly. I prefer to interact and for people to, I think it's much better if the audience will understand something small than if they just get an overview of something big. So I can probably use up all the time, but if you don't want me to use up all the time, if you want to go and attend the last session of one of the other tutorials or something, or you think I'm just going too slowly and boringly, then just let me know. Okay. Any questions before I actually get started? I think we've already had, just from the discussion, some interesting overview of what people are interested in and want consider to be important about. Okay, yeah, this eraser is not working very well. I'm hoping that at the lunch break, somebody's going to be able to bring one of those squirty bottles that you can actually erase the whiteboard with. Okay, so I'm going to start at really the very foundation of log linear models, conditional random fields, which is maximum likelihood. And I'm using, these are my lecture notes, I'm using them as prompts. I'm going to say things that are not in here, but the most important things that I say are in here. So maximum likelihood is a principle of induction. So this is really the foundation of machine learning and also the foundation of statistics, that we have data, and then from that data we want to jump to a conclusion. And fundamentally, so we're jumping to a conclusion, we're detecting patterns in the data, or we're finding a model. And fundamentally, the data do not determine the model. The model is only determined by the data together with a principle of induction. And this principle, it's not really an axiom, because it's not something that and it's certainly not a theorem. It's not something we can prove. It's really a behavior that we intend to adopt. Okay, and so what's the scenario? And I'm making this very general. So we have training data, x1 up to xn. And these are our training examples. Each xj belongs to some set x, and I don't need to specify what that set x is. Very commonly, x is a Euclidean space. Very commonly, x is r to the d for some d, and each training example is a fixed length real valued vector. But I don't need to assume that. And then we have some prior knowledge. which is that each xi follows some probability distribution f theta. And so there are different ways of really thinking about machine learning, but I'm thinking about machine learning using probability theory. And I said we have our training data, we're going to have our principle of induction, but we really need something additional, which is an assumption about how the world works probabilistically. And so this assumption is that the xi's all follow a distribution that's in a family. So what I really have here is a family of probability distributions. And theta is the parameter, and as you change theta, you get different distributions in the family. And my assumption might be wrong. The xi's might follow a distribution that is not a member of this family. And if that assumption is wrong, then really all bets are off. And then the goal of learning is to identify the best theta, which I'll call theta hat. So theta hat is going to be my estimate of theta, which is based on my training data. And so I'm not even allowing for the possibility that theta is outside this family. And then a principle of induction, so just call that PI. So PI is a method for selecting a sensible theta hat, which is going to be based on the data. And okay, any suggestions for what's a sensible way to choose a theta hat? I'm used to having more space. So, come on. Just, what's a sensible way of choosing theta hat? Maximum likelihood. What does maximum likelihood mean? Say it in ordinary English.
We choose the model that maximizes the likelihood. Under this model, the likelihood of the data is maximized.
Yeah.
It has the highest probability.
Yeah. So I said maximum likelihood. I didn't say what likelihood is. But I'll say, so maximum likelihood, choose theta hat equals argmax over theta of probability of x1 to xn given theta. So this is all theoretical, but if I could take my training data, evaluate the probability of the training data according to each member of the family, and some members of the family are going to say that the training data have higher probability. Well, I'm going to choose the member of the family that says that the training data has the highest probability. So now I'm going to make an assumption, which I'm going to ask you to tell me what the assumption is. And based on this assumption, I'm going to get that theta hat is the argmax over theta of the product from I equals 1 to n of the probability of xi given theta. So what's the assumption that I need to make in order to get this expression for theta hat? I need to assume that the x's are independent. So assume the xi are independent. And is this give me an example of a scenario where this assumption is reasonable, and give me an example of a scenario where it's not reasonable. Okay, if you work with David Jensen, you should be easy for you to think of examples in both directions.
features, then if you're looking at a sentence, then words are not actually independent of each other.
Okay, let me clear up a confusion. These xi's are data points. They're not features. So typically each of these xi's will be, so most commonly each xi would be a whole vector of feature values. So, so my notation, I'm going to use the bar notation to indicate vectors. And so x bar is a vector, I'm using angle brackets for that, of feature values x1 to xd, where d is the dimensionality. And then if I am talking about more than one example, I'll call that x bar I. And then this is going to be xi1 up to xid. So here, these x's are whole examples. So the question is, what's a realistic scenario where the training examples x bar would be independent, and a realistic scenario where the training examples x bar would not be independent?
Going with his sentence labeling, and
Yeah.
if you have multiple sentences in the same paragraph, they're going to look at it as
Yeah. So multiple sentences in the same paragraph, actually, they might not be entirely independent because they're going to be talking about the same subject matter. They're going to be written by the same author. Or a different example, one that is occurring to me just now, supposing that these examples X are people, individuals. And one data set might be, people with a certain disease from a certain hospital. And those people, you could assume, are more or less independent. If this person gets lung cancer and comes to the hospital, that's going to be independent of this other person getting lung cancer and coming to the hospital and therefore becoming part of the training set. But supposing that the individuals, say, are mortgage fraud criminals. The mortgage fraud criminals have been identified by some investigative process, and that investigative process, maybe it takes you from one criminal to the next criminal to the next criminal. And so all these criminals are going to be related to each other, possibly related because they engaged in similar types of fraud. And just because you have just because you have an FBI data set of 100 mortgage criminals and all the mortgage criminals are from Southern California, that doesn't mean that there are no mortgage criminals from other places. It just means that the identification was limited to those ones, and so they're non-independent in that way. So this is a big assumption that the training examples are independent. But it's one that's very common in machine learning. And if the training examples are independent, then the probability of the set of them is the product of these probabilities. And then the principle of maximum likelihood says that we should choose a theta to maximize this product. Okay. So why is this called maximum likelihood? So it's clear why it's called maximum. The reason why it's called likelihood is because of some terminology. So we're just going to write that the likelihood of theta semicolon x by definition is the probability of x semicolon theta. And I guess I should explain something else about notation. So this vertical bar means conditional probability. And so if theta are the parameters of my distribution, then for different parameter values theta, I'm going to get different probabilities. And so it's reasonable to use the conditional notation when I have a data point on the left-hand side and parameter value on the right-hand side. And if I was a Bayesian, then I could talk about the probability of the parameters given the data. But if I'm not a Bayesian, then I don't view parameters being a random variable, and so I shouldn't use the notation probability of theta given x. And so if I'm not a Bayesian, the notation I'm going to use is semicolon. And semicolon really just distinguishes the data from the parameters. So And so this is just a very simple notational convention. But this capital L function is called the likelihood function. And the reason for the notation is that if I think of theta as being fixed, you know, nature chose some probability distribution theta, and then nature chose a random sample and gave it to me. So if you think of theta as being slowly varying and x as being rapidly varying, you'd use this notation. But if you think of the x's as being fixed, and then you're considering different thetas, you'll use this notation. And so this big L stands for likelihood. That's the likelihood function. And something that people sometimes get confused about. So this probability, it can be a probability mass or it can be a probability density. If the x's belong to a discrete space x, then they're going to have probability masses. And if they belong to a continuous space, they're going to have probability densities. And here, so we're multiplying all these probabilities together. And if they're probability masses, then we're going to be multiplying numbers together that are less than 1. And these probabilities, so the product probability is going to be a number that is very small, much less than 1, but still positive. And so actually, computationally, if you want to implement this, typically you would take the log of the probabilities and you'd be summing them, and then you don't get numerical underflow. If the x's belong to a continuous space, like Euclidean space, then the probability densities can be bigger than 1. And so actually the likelihood can be bigger than 1. So it's not a bug in your software if the maximum likelihood is bigger than 1. Okay. So theta hat is the argmax over theta of the sum from I equals 1 to n of the log likelihood of theta and then x bar I. The logarithm function is monotonic and strictly increasing, and so maximizing the product of likelihoods is precisely equivalent to maximizing the sum of likelihoods. So this is called the log likelihood, and the principle says that we want to maximize the sum of log likelihoods. Okay. So if that's clear, then I can move on to an example which is going to be relevant to logistic regression. And this is a very well-known example, but it's still worthwhile to work it out. For anybody who hasn't seen this derivation before, it's got some twists and turns. We're going to work out the maximum likelihood estimate of the parameter theta of a Bernoulli distribution. What's a Bernoulli distribution? It's a coin flip. And so it's a special case of a binomial distribution. A binomial distribution is the distribution of the number of successes if you do n coin flips. And the Bernoulli distribution is the number of successes if you do a single coin flip, so n equals 1. Let x be a Bernoulli random variable. Remember the notation, capital letters for random variables and then lowercase letters for outcomes of random variables. I guess it's a conflict of notation. Before I used capital X for the space of all possible outcomes. So here, X is the random variable, and its possible outcomes are 0 and 1. So those are my names for heads and tails. And so, we have it's a discrete distribution. So it's a probability mass function as opposed to a probability density function. And so probability of x equals x equals, so here's the random variable x, and here's its possible outcomes, which are either 0 or 1. So can somebody tell me what's the formal way of stating the probability of the different outcomes for a Bernoulli distribution with parameter theta?
Yeah. Theta that equals 0 and 1 minus theta equals 1.
Okay, so I'll say theta if x equals 1 and 1 minus theta if x equals 0. So you could put it the other way around, but this is what's in my notes. Okay. And so now already I'm going to do a trick. I'm going to write this as theta. Okay. Theta to the power x times 1 minus theta to the power 1 minus x. This is really just saying the same thing as this. It's just that this says it in notation that's going to be more convenient for future use. If x equals 1, then theta to the power 1 is theta, and 1 minus theta to the power 0 is 1. So this is theta times 1 if x equals 1. And if x equals 0, then here we get 1 times 1 minus theta. So this says the same thing as this. It's just a notational trick. Okay, so now let's suppose we have a training set. So training set x1 through xn, and each xi is either 0 or 1. Then I want to maximize the likelihood function, so I need to write it down. The likelihood of theta given x1 to xn is so what's the likelihood function? And this is the likelihood, not the log likelihood. Somebody tell me the formula for the likelihood. Yeah?
Product of likelihood to the exponent sum of the xi's.
Okay, so that's the simplified version. So the direct definition of likelihood, if the examples are independent, is the product of the probabilities. So product of theta to the power xi, 1 minus theta to the power 1 minus xi. And then this is theta to the power h times 1 minus theta to the power n times 1 minus theta to the power minus h, where h is the sum of the xi's. So there are three things in here. There's theta to the power xi, there's 1 minus theta to the power 1, and there's 1 minus theta to the power minus xi. And when I take all those products, and I get each of those three things n times. So 1 minus theta to the power 1, n times I get 1 minus theta to the power n. And here, these xi's, some of them equal 1, in which case I get a theta. Some of them equal 0, in which case I get just a 1 in the product. So what I end up with is theta to the power, the sum of the xi's. And similarly here is 1 minus theta to the power minus the sum of the xi's. And so now theta hat is the argmax over theta of this thing, which is theta to the power h, and 1 minus theta to the power n minus h. We have that 0 is less than equal to theta, less than equal to 1. So this is a little bit of an awkwardness. So the parameter theta, it's not allowed to be any real number. It has to be a real number between 0 and 1. And so this maximization problem, it's not an unconstrained optimization problem, it's a constrained optimization problem. And generally speaking, constrained optimization problems are harder. You have to introduce Lagrange multipliers or other technicalities to solve them. This particular problem I can solve rather directly. But still, whenever you're doing a maximum likelihood, one thing you need to pay attention to is whether it's an unconstrained optimization problem or constrained. Okay, so what's the simplest possible way of solving mathematical optimization problems that you typically learn as a freshman? Take the derivative, and then what? And set it to 0. So, that's a strategy that doesn't always work, but it's a good first attempt. So, since I'm talking about machine learning, which I view as being part of computer science, I'm going to, as opposed to part of mathematics, I'm going to call this an algorithm. So, compute derivative and solve for equal to 0. Pretty much all the calculations I'm doing here with this Bernoulli example, I'm going to do them again in more generality for log linear models and conditional random fields. So what's the derivative? So what I need is the derivative d by d theta of theta to the h 1 minus theta to the n minus h. And let me point out, so this is at the bottom of page 3 in the notes, and there's a typo in the notes. So it says d by dp, but what I actually mean is d by d theta. And and I have a notational question. So this is the curly d for derivative instead of the regular d for derivative. And what's the difference in meaning between a curly d and a regular d for derivative? Partial versus single parameter. So if you have a function, say f, which is a function of a single argument, say z, then that function only has got one derivative, the derivative with respect to z, and you can call that d by dz. But if you have a function which has more than one argument and it's got a derivative with respect to each of its arguments, and so you use a curly d to indicate the derivative with respect to any particular argument. And something that is quite a common phenomenon here when we're dealing with maximum likelihood is that there's some ambiguity about how many arguments your functions have. Because you think of some arguments as being fixed, and then and if an argument is fixed, then it's not really an argument. But you can always then say, well, suppose it's not fixed. And then you could take the derivative with respect to that. So here, this likelihood, so we're thinking of the xi's as being fixed. So we're not going to take the derivative with respect to them. But there's something which is even more fixed than the xi's, which is n. Because even before we drew the training set, we knew that there was a constant n of how many training examples we were going to draw. So in a sense, this function, it's a function of n, it's a function of the x's through h, and it's a function of theta. But n I'm thinking of as being totally fixed, and then h I'm thinking of as being fixed for the time being. And really the only thing I'm thinking of as being varying here is theta. So I could write d by d theta, but I chose to write curly d by d theta. But it's always, you should always ask yourself, so well, what is fixed and what is not fixed? And there can be degrees of fixedness. Okay, so now I'm just going to work out this derivative. And there's the derivative of product. So the mnemonic is fg prime is f prime g plus fg prime. And then f composed with g prime is, it's f of g prime. So now f prime of g times g prime. So this is the chain rule for derivatives. This is the derivative of product. So what do I get here? And then, so if I want the derivative of theta to the h, that's just a monomial. So that's h times theta to the h minus 1. So I get h times theta to the h minus 1 times 1 minus theta to the n minus h. And then here the theta h stays fixed. And I get n minus h times 1 minus theta to the n minus h minus 1. And then I need a minus 1 because I had a minus theta here. I'm going to, so this is the sum of two terms. I'm going to write it as a single term. So that's equals theta to the power h minus 1 times 1 minus theta to the power n minus h minus 1 times h times 1 minus theta minus n minus h theta. So this is just rewriting this expression. And now, so I've got the derivative. Now I want to set it equal to 0. So the derivative equals 0 if, and there are three cases. What are the three cases? Sorry? Yeah. So first case is theta equals 0. Second case is 1 minus theta equals 0. Third case is h times 1 minus theta equals n minus h theta. And these two cases, in these two cases, the whole thing equals 0. And remember, what we're talking about here is the thing that we're so remember two things. First is that we're maximizing, and second is that we're dealing with a likelihood, which is a probability. So we're trying to maximize something, and because it's a probability, it's always going to be bigger than or equal to 0. So, so these two cases must be minimums, or minima. So these are minima. So they're solutions for the derivative equal to 0, but they're not the solutions we're interested in. And then this case, so we have h minus h theta equals n theta minus h theta. We can cancel the h thetas, and we get theta equals h over n. And this is the maximum. You can check that this is a maximum. So have actually solved the maximization problem by setting the derivative equal to 0 and by picking the right solution for the derivative equal to 0. What does this solution say in practice? So theta equals h over n. Is that?
Number of positives over the total number.
It's the number of positives over the total number. So your maximum likelihood estimate of the probability that your coin is going to come up heads is the number of heads that you did observe divided by the total number of coin flips. So it's very intuitive, and so what this example shows is that the principle of maximum likelihood agrees with intuition, at least in this very simple case. Yeah.
One question. So, is there somewhere written, proofs elsewhere in machine learning world that says this kind of maximum likelihood functions always converge to the real distribution, convergent distribution to the real case? So, is that a particular reason why you want to estimate your parameters this way? You can always match the second moment, match the nth moment, and then you can do all those. Why particularly this one?
So I think it's an excellent question. I think the question you're asking is why the principle of maximum likelihood? And I haven't answered that question. I hinted at it when I emphasized that that maximum likelihood is a principle. So it's not an assumption. I'm not saying that this is the way the world operates. And it's not a theorem. It's not something that I can prove from other axioms that are more primitive. It's, I think of it as being a behavioral principle, an operational principle. And if you think of the difference between computer science and mathematics as, mathematics is about proving things, and computer science is about algorithms, about actually doing things. Well, then the principle of maximum likelihood really, it's a high-level algorithm. So, then we can prove that the algorithm has various properties, but we can't prove that it always gives an answer that is always the correct answer. And in fact, the principle doesn't even always give answers that are sensible. And I can give an illustration of that. This is worth knowing. I was talking at the beginning about what my goals are when I teach a graduate class, and one of my goals is to that people should know things that are important, even if they're not directly related to the topic of the class. This is maximum likelihood pathology. So a pathology means something that can go wrong. So any of you know a maximum likelihood pathology? A simple example where maximum likelihood gives an answer that is intuitively wrong?
One case would be, let's say that we have a continuous distribution.
Yes.
And we only have 1 point.
Yes.
So in that case, if we think of it as a bell-shaped Gaussian, maximum likelihood would give us will tend to increase to infinity.
Yes. Yes.
To infinity.
Yeah.
By centering over that particular.
Yeah. So let me take a minute to explain that example, then I'll explain a variation of it that I think is a little bit more complicated, but an even better illustration of where maximum likelihood just gives an answer that everybody would say is wrong. You know what Gaussian distributions are. And if I have my points, which are in, say, R squared, so here I have some data points, and then the Gaussian distribution is going to look like sort of a Mexican hat, where the density you can view as being on the axis that comes out of the board like this. And I can draw that Gaussian distribution with contour lines. So if there was a Gaussian distribution that fitted these points, then the contour lines might look like this. So see, the distribution, the Gaussian is centered on the mean of the data points, and then as I go further away from that mean, the probability of getting a point that's further away from the mean declines. And so, and see, this Gaussian distribution, it gives a high probability to each of these 4 points. It actually gives an even higher probability density to a point that's right in the middle. And so if I wanted to predict where my next sample would lie, the most likely location for the next sample is here, right in the model. Okay, and if you have data points like this and you fit a Gaussian to them, then with the principle of maximum likelihood, so you say which Gaussian gives these data points the highest probability, you get a very reasonable answer. But supposing that you have a single data point and you try to fit a Gaussian to that. And you want to fit the Gaussian that gives a single data point the highest probability. That's the principle of maximum likelihood. What Gaussian are you going to get?
Basically, going to have a standard deviation of 0.
Basically, you're going to get a Gaussian which has a standard deviation of 0, which says that the probability of getting any point that is any distance away from this one is 0, and the probability density of this point will be infinite, because a probability density function, the area or the volume under the function equals 1. So if the support of the function is 0, you have a standard deviation of 0, then the density has to be infinite. So maximum likelihood, you give it a single training point, it'll say, well, the probability of getting any future point that's any different from this is 0. And so this is probably the simplest pathology of maximum likelihood. But it's not my preferred pathology, because you could answer, well, this is a pathological situation to begin with. How can you do machine learning from just one data point? It's not something you would try to do in practice. But here's a very common machine learning situation. You're trying to do clustering. So maybe my data points look like this. And the model that I want to fit is a mixture of 2 Gaussians. Essentially, I want to say, well, there's a region of high density here, and there's another region of high density here, and then in between, this is all area of low density. So I want to cluster this data set. And and I know that I want to use k equals 2 clusters, and each cluster should be a Gaussian. So it's a pretty narrow and well-defined problem. And intuitively, this would be a good solution. 1 Gaussian here, 1 Gaussian here. But does anybody know what the principle of maximum likelihood actually says in this case? If you did maximum likelihood estimation of the mixture of 2 Gaussians, what would you get? Yeah?
A line.
No. Okay. So I'm talking about unsupervised learning. And specifically, I'm talking about clustering. I'm not thinking that these are one class and these are another class and I want to separate them. If I wanted to separate them, then I could use 1 Gaussian for each class, and then I'd get a line, I'd get a straight line, maybe I'd get a conic section, I'm not sure to separate them. But this is just unsupervised, just clustering. Well, the answer as to what you'd get as the outcome is, imagine having 1 Gaussian that is centered on a single point, and then another Gaussian that is very spread out over all the data. Then this big green Gaussian is going to give a non-zero density to every data point. And this little green Gaussian that is tightly centered on a single point is going to give infinite density to that single point. And when I multiply together the non-zero density of every point with the infinite density on this point, I get an infinite result. So the principle of maximum likelihood says that the best way to cluster data is to use one cluster to give infinite likelihood to one point, and then to use the other cluster to give non-zero likelihood to every point. And I don't think anybody would say that that is that's the intuitively desired or reasonable clustering. Intuitively, you'd like each cluster to handle a fair number of points. You don't want a single cluster to handle a single point, even if it can give infinite likelihood to that single point. And so to me, this is a very clear pathology of maximum likelihood. And there are various ideas for modifying the principle of maximum likelihood so as to resolve the pathology. But that's not something that I'm going to be getting into now. Okay. So if there are no questions on that, I'm going to move on to talk about conditional likelihood.